Hello everyone, this is Andrew Watkins, Carter Allen, and Megan Cullen Meyer here with problem 1. Just as a heads up, this is a disclaimer that these crappy drawings are not drawn to scale, so anything you see here is just a rough estimate of the distance or how big something is. So we have a spring here. It is 20 centimeters is its natural length. I put lazy length here just to be funny for you. So we have a force of 40 newtons, and it's required to stretch the spring a length of 30 centimeters. That's 30 centimeters right there. So there's 20, and to stretch it an extra 10, it requires 40 newtons. And just as a heads up, since this whole thing here is in newtons, we're going to switch them from centimeters to meters, so you'll start to see them in decimal points, so you'll see 20 centimeters is 0.2 meters. So how much work is done in stretching the spring from 35 centimeters to 38 centimeters? That's our question, okay? That's what we want to find out. So what do we know here? We know that a spring's constant is given by force equals K times X, and we can rewrite that as K equals force over X, and we'll do that a little bit later on down the sheet here. Our force is 40 newtons, we know that. Our distance in meters is 0.3 minus 0.2, and this is the natural state minus the extended state, equals 0.1 meters. And therefore, 40 equals 0.1 K. So our constant, or our force, is 400 newtons per meter. With me so far? Cool. So, if work equals force times distance, and force equals K times X, and D equals, or the distance equals, delta X, work equals K times X times delta X. So what do I want? I want the work done to go from here to here. How much work is done to stretch the spring out this much, basically? Our natural state's here. How much work does it take to stretch the spring out this much on this interval? So now let's set up the general equation, and let's use some calculus here, all right? So we have work equals the integral from a to b of K times X dx, all right? So this will allow us to find the work done on the specific interval from this interval to this interval, right here. Boop. So now let's solve this very, very difficult general equation. Let's do that together here. So the first thing we do with anything, right, is we pull out, well, not with anything, but with doing your integrals, is to pull out the constant. So K is our constant, so we'll pull that out. And so we have K on the interval a to b, integrating x dx. And what do we get? I'm not going to do this out, guys. Come on. This is Calc 2. So our final answer here for the general equation is our constant times 1/2 x squared on the interval from a to b. And that's our solution to the general equation. And now, who wants to plug in some particular info with me, huh, guys? Let's do that together. All right? Sounds good. So K equals 400. Great. And what's A? This is really important here. So A is our 35. Remember we had 35 centimeters minus the natural, or that kind of lazy length that we were talking about in the beginning, and that equals 0.15 meters. It's 15 centimeters. And the end of the interval is 38 centimeters, or 0.38 meters, minus, again, the natural length of the spring equals 0.18. So with our general equation solved, we have work equals 400 times 1/2 x squared on the interval 15 to 18. Okay? When we plug that in, to do algebra, again, I don't have time to show you how we do all this algebra, just plug it into your calculators here. We get, oh, the suspense is killing me. Should I turn the page? What do you think? Oh, man, I'm so excited. What's our answer? Bam! 1.98 joules, because we're working with newtons and meters here. So the amount of work required to move our spring from 35 centimeters, or 0.38 meters, 0.35 meters to 38 centimeters is 1.98 joules. There's your sentence, and there's your numerical answer. Thank you, and have a fabulous day.